Hello and welcome to Scholar Fedu. This is our UTME prep series where we provide relatively detailed solutions and explanations to the UTME exam. And in this recording, we are looking at the UTME questions for physics for the year 2017. This is the second part of the recording where we are going to be looking at the last 20 questions. Before we continue, don't forget to subscribe to our channel, like and share our content, and visit our website at scholar.com to pass the UTME exam for free. The first question here on optics. In the diagram above, which of the angles theta 1, theta 2, theta 3 and theta 4 is the angle of deviation of a ray of light passing through x, y, z? Alright, so if we look at this diagram here of a light ray passing through a triangular prism, you see that the angle here, okay, is labeled the angle of deviation. And if we relate that to the diagram that we have right here, see that that corresponds to the angle theta 3. So the theta 3 here, okay, this angle here theta 3 is the angle of deviation. Next, on quantities, which of the following is the dimension of pressure? Alright, so pressure, the formula for pressure is force over area. Okay, so we need to look at what is the dimension of force and what is the dimension of area. Now, force, area, let's start with area, which is easier. Area is, let's say, take the area of any body, let's say rectangle, length times breadth. So we have length measured in meter, and dimension of anything measured in meter is capital L. Okay, breadth also measured in meter, dimension of anything measured in meter, like I said, is capital L. So we have L times L, that's L square. Then we look at force. Force is mass times acceleration. The unit for mass is what? Kilogram, and anything measured in kilogram, and that can only be mass, is the dimension is capital M. Okay, acceleration, the unit of acceleration is meter per second square. We can use this unit here to get the dimension of acceleration. So meter, anything measured in meter, the dimension is L. Seconds, anything measured in seconds, that's S, and that can only be time, the dimension is capital T. So this will be LT per, like L per T square, because this is minus 2 here. So we have M times this, and this will give us ML per T square. So this is the dimension of force. Then we go back to our formula that pressure is force over area. So we look at what the dimension of force, we have it here as M, okay, ML per T square, okay, divided by the dimension for area, which is L square. So here, this L will cancel one of this L here. So we are going to have one L remaining here. So this will now become M per T square per L, or you can just write this as M per L per T square. So ML raised to power minus 1, T raised to power minus 2. This is the dimension for pressure. Next, on electricity, a capacitor 8 microfarad is charged with a potential difference of 100 volts. The energy stored by the capacitor is, alright, so the capacitance is 8 microfarad. The capacitance of that capacitor is 8 microfarad. Its potential difference is 100 volts. Okay, that's what we have from the question. There are different formulas for finding the energy stored in the capacitor. Okay, the one we'll be using here is this: E is equal to half CV square, where C of course is the capacitance and V is the potential difference. So we now substitute for C and V here. So we have this will be 1 over 2 times 8 micro. See, I have not removed that micro here. Why? Because that micro itself has its own value, okay, which we are still going to use, but for now let's just leave it at micro. Alright, times 100 square. This will then be 1 over 2, like 2 here, 2 in 8, that is 4. So we have 4 micro times 100 raised to power 2 means 100 times 100, so that is 10,000. Now 1 micro, the value of 1 micro is 10 raised to power minus 6, so you have to bring that back here now. So now say this is 4 times this micro, 10 raised to power minus 6 times 10,000 is 10 raised to power 4, because we have 4 zeros here. Then we use our law of indices on these two here. 10 raised to power minus 6 times 10 raised to power 4. It has the same base 10, so you are going to take that common base. Then when you have multiplication, what we do is what? We add the powers. We add the powers together. So you have minus 6 plus 4. So this will be 10 raised to power 4 times 10 raised to power minus 6 plus 4, that is minus 2. Next, on electricity, the net capacitance in the circuit shown above is. So if you look at this circuit here, these two capacitors, they are connected in parallel. Okay, then this parallel connection is now in series with this other capacitor. So what we are going to do is this: to find the net capacitance, we look at what is the effective capacitance for these two that are in parallel. And when you have capacitors in parallel like this, to find the effective capacitance, we simply add up the capacitances. So for this one, the effective capacitance for these two capacitors in parallel, let us represent it as Cp. It will be equal to 2 plus 2. So that is equal to 4. So we have 4 microfarad. So that means that the effective of this capacitor now, 4 microfarad, is now going to be in series with this other one here now. Okay, so we now find the net capacitance, okay, for both of them. So this, we assume it is now 4 microfarad in series with this. So when you want to take the effective capacitance for capacitors like that in series, you just say, so let's say you have two capacitors now, like this 4 microfarad, and the effective of this one's 4 microfarad. So let's say it's capacitance 1 and capacitance 2. We simply say that the effective capacitance C is, we get it by 1 over C is equal to 1 over C1 plus 1 over C2. So that C1 is going to be the effective of these two here, which is that 4 that I've calculated here, plus 1 over C2. The C2 is going to be this second capacitance here. Alright, so you have 1 over 4 plus 1 over 4. Since the denominator is the same thing in this fraction, we can just add up the numerator. We add up only the numerator. So you have 1 plus 1, that will be 2 over 4. Okay, we are doing that because the denominator is the same thing, so we don't need to take all LCM and all of that. We just add up the numerator. So here now we have 1 over 6 equal to this 2 over 4. If you reduce it to the lowest fraction, that's dividing the numerator and denominator by 2, you are going to have 1 over 2. So 1 over C is equal to 1 over 2. That means that your C is equal to 2. That means that's if you compare both sides of the equation. So you have the net capacitance there to be 2 micro. Next, a sonometer wire of length 100 cm under a tension of 10 Newton has a frequency of 250 Hz. Keeping the length of the wire constant, the tension is adjusted to produce a new frequency of 350 Hz. The new tension is. Alright, so the frequency, it varies directly as the square root of the tension. Frequency varies directly as the square root of tension. Now, if you remember Charles' law, for example, let me use Charles' law to just explain what we have here. In Charles' law, remember that we have volume is directly proportional to temperature. Volume directly proportional to temperature if the pressure is constant for a gas, for a given mass of gas. Now, when you turn that into an equation, it becomes V1 over T1 is equal to V2 over T2. Now, in this case, instead of volume and pressure, we now have frequency varying directly as tension. So we have frequency and tension here. Okay, then this is not just ordinary tension, but the square root of tension. So the equation is also going to follow like that Charles' law, like that V1 over T1, but this one is going to be F1 over root T1 because it is the square root. Okay, for this one here, for the tension, it's the square root, not just the tension. So we're going to have F1 over root T1 is equal to F2 over root T2. If we now look at this question here, the initial values that we have is the length was originally 100 centimeter under a tension of what? Of 10 Newton. So we take note of that. F1, these are the initial values, 250 Hertz, tension 10 Newton. Then the pressure now changed, okay, to 350 Hertz. So we have to find the tension at that pressure. The frequency rather changed to 350 Hertz, and we have to find the tension at that pressure, or the tension that produced that frequency. So the frequency here now is 350. You are looking for T2. You just substitute into this formula here. So F1 over T1 will be 250 over root 10, okay, equal to 350 over root T2. Then we are going to square both sides. The reason we are squaring both sides is because we want to remove the square root of this T here. So if I square this side now, that means I'm going to have 250 square, which will be 62 times 2,500. 62,500. Then if you square this root 10, that square is going to remove the root here, so this will be ordinary 10. Okay, on this side I'm going to have 350 square, and that will give me what you have here, 122,500 divided by root T2 square will give you just root T, will give you just T2. Okay, so that square will be removed. The next thing I'm going to do is to cross multiply. Okay, cross multiply the denominator here, cross multiply with the numerator here, the denominator here with the numerator here. So I'm going to have 6 to 500 times T2, okay, and that gives me this, and 122,500 times 10, so you have 122,500. Then we divide both sides by 6 to 50, and then I'm getting 19.6. okay. Next, on sound wave. In a sound wave in air, the adjacent rarefactions and compressions are separated by a distance of 17 cm. If the velocity of the sound wave is 340 meters per second, determine the frequency. Alright, I think we are quite familiar with this formula here. Okay, V is equal to F lambda, where V here is the velocity of the wave, F is the frequency of the wave, and this lambda here is the wavelength of the wave. And in this question, we have to determine the frequency. So what we do here is try to make this frequency the subject of the formula. And how do we do that? We are going to divide both sides of this equation by lambda. That means that on this side I'm going to have V over lambda is equal to, on this side I will have F lambda over lambda. Then lambda will cancel lambda on this side, so I will have just V over lambda is equal to F. Or I can write that as F is equal to V over lambda. So this is the formula that I'm using now. The velocity you are given directly in the question as 340 meters per second, so we have that already. However, they didn't give us the wavelength explicitly. They did not give us the wavelength. So how do we get the wavelength? In a longitudinal wave like sound wave, the distance between the rarefaction and compression is half of the wavelength. Okay, is half of the wavelength. That means that the wavelength is going to be 2 times the distance between a compression and a rarefaction. Okay, so we have 2 times the distance that we are given here, the distance of separation between this rarefaction and compression. That's the distance between them. This is 17 centimeter. So we have 2 times 17 centimeter, and that is equal to 34 centimeter. However, if you look at what we have here, the unit is in centimeter, but the unit of the velocity here has what? Meter in it, right? Meter. There needs to be a balance between the units that we are using. We cannot use meter directly with centimeter. Okay, they are not, it's not like, let's say they are not the same currency. Okay, so what do? We need to convert this centimeter to meter. And how do you convert from centimeter to meter? By dividing by 100. You divide whatever you are given in centimeter by 100 to get its equivalent in meter. So we divided this by 100 and we have 0.34 meter. So this is what we are now going to substitute in the formula. So we have the velocity 340 divided by 0.34, and that gives us 1000 hertz. Next, also on sound wave, a note is called an octave of another note when its frequency is twice that of the first note. Okay, when its frequency is 2 times the frequency of the first note. We have a website at scholar.com where you could practice exams for free, the UTME exam and the post UTME exam. It also features modular quizzes in physics, chemistry and biology. So if you've studied a topic in any of the subjects and you want to test your understanding of the topic, you can head on to our website at scholar.com and take modular quizzes for free. Also, if you sign up on the website, it has a personalized dashboard where you could use to check your progress in learning. We also have interactive sessions on the website and on our social media platform. Freebies are also available to top performance on the website. Next, we have a metallic strip of iron and brass was heated. Which of the following diagram accurately illustrate the shape of the strip after heating? This is a question on expansivity. Okay, on expansivity. Now, if you look at this diagram here, okay, so let's say we have a bimetallic strip. Okay, a bimetallic strip like this. So we have brass and we have iron. When this metal is heated, okay, when they are heated, when this strip is heated, these metals are going to expand. Okay, they are going to expand. They will bend. Their length will become, they will become longer than they originally are, and this is how they bend. This is how they bend. So if you look at that bending, you can see that the brass bends more than the iron. Okay, that means that it has a greater linear expansivity. It has a greater linear expansivity. Since it bends more than the iron there, it shows that it has a greater linear expansivity. So the correct illustration is what we have here. okay, in this diagram here. Next, on equilibrium and moment of forces, which of the following is in a neutral equilibrium? A cone resting on a slant edge is said to be in neutral equilibrium. Also is a ball. For example, you have a ball or a sphere that is on an horizontal ground, a plain ground. That's also a state of neutral. The ball is said to be in a state of neutral equilibrium. But if you have a cone that is resting on its tip, that pointed tip, that's an unstable equilibrium. Or a ball that is on the curved edge. Let's say you have a bowl. You know how the back of a bowl is. A bowl is usually like this. So if you turn that bowl upside down and now put a ball on top of it, okay, that is going to be a state of unstable equilibrium. Let me draw some diagrams to illustrate this. So a cone on a slant edge like this. You have a cone on a slant edge like this, resting on a slant edge like this. Okay, this is neutral equilibrium. Or you have a ball on an horizontal ground like this. That is neutral. But if you have a cone resting on its tip, something like this, this is the tip of the cone. So you have a cone resting on its tip like this. This is a state of unstable equilibrium. The cone will be unstable, okay, in this state. Or you have a concave hole like this. Sorry, you have a concave hole and you have a ball on it. Okay, you have a ball on this. Is unstable, instead of unstable equilibrium. But stable equilibrium is if you have a cone, okay, resting on its base, on its flat base. Okay, this is stable equilibrium. Or a ball in the middle of a concave bowl. A ball in the middle of a concave bowl. This is stable equilibrium. Okay, so these diagrams that we have here is for neutral equilibrium. This is for unstable equilibrium. This one and this one. Okay, don't mind this. Why this one is for stable equilibrium. Next, a convex mirror is used as a driving mirror because the convex mirror is preferred for use as a driving mirror over the concave mirror because one, the image that it produces is erect. The second thing is that it also has a large field of view. That means that when you're using a convex mirror, you can see a whole lot of things, a wide range of things, okay, in that mirror, compared to if you are using, a concave mirror. But here, it has a long focal length. That is not exactly true. It depends on the curvature of the material from which that mirror has been made. Okay, the radius of curvature of that material. That's what will determine. Okay, that's what will determine the focal length. But we can say of the image that it is erect and that the mirror gives you like a wide range of view, where it covers a large field of view. So you have I and I only. Next, on electricity, what is the cost of running 5 50-watt lamps and 400 watt lamps for 10 hours if electrical energy costs 2 kobo per kilowatt hour? Okay, the first thing we need to do here is to calculate the total power that is consumed. Now we are running 5 50-watt lamp. Okay, so if you look at what will be the total power that will be consumed by 5 50-watt lamp, that is each of those lamps has like 50 watts. So if you have 5 of them, then that means they will consume a total of like 5 times 50 watts. Okay, that's 250 watts. Then we have 400 watt lamps, that is each of those lamps is 100 watts. So you have 4 times 100, so that will be 400 lamps. So these lamps here will consume 250, that's 5 times 50. These ones will consume 400, that is 4 times 100. So 250 plus 400, we are having 650 watts. That's what they will consume. Okay, all of those bulbs will consume, all of those lamps will consume 650 watts. Then we convert this to kilowatt hour. Okay, kilowatt hour. So how do you convert from watt to kilowatt hour? We divide by 1000. So if you divide this by 1000, you are going to get 0.6 kilowatts. Then we are given that these lamps, okay, they run for 10 hours. So the electrical energy that they will consume will be the power that they consume times time. Q represents electrical energy, and it will be equal to the electrical power, okay, the power consumed, total power consumed times time, and that here will be equal to the total power here is 0.6 kilowatts times 10 hours. So that will become 6.5. That is 0.65 times 10. That's 6.5 kilowatts hour. Now in the question they said electrical energy costs 2 kobo per kilowatt hour. What that means is that 1 kilowatt hour is equal to 2 kobo. So what will be the cost of 6.5 kilowatt hour? That will be 6.5 times 2. You just multiply it by the cost of 1 kilowatt, because we can write this 6.5 kilowatt hour as 6.5 times 1 kilowatt hour, and 1 kilowatt hour is what? 2 kobo. So that means I'm going to have 6.5 times 2, or 2 times 6.5, and that is equal to 13 kobo. Okay, 13 kobo. However, if you look at what we have here, the amount is in what? Is in naira. It is in naira. So how do we get, okay, 13 kobo in naira? How do you convert to naira? We know that 1 naira is 100 kobo. 100 kobo is 1 naira. So if I want to convert from kobo to naira, that means I'm going to divide by 100. It means if I have 100 kobo now, okay, I divide that by 100, I'm going to have 1. So that means 1 naira. 100 kobo is 1 naira. If I have 200 kobo, that will be what? 200 divided by 100. That's 2 naira. So here I have 13 kobo. It was even less than 100. I'll divide it by 100, and I'm going to have what is 0.13 naira. Next on it, and its calorimetry. The specific latent heat of vaporization of a substance is always greater than the specific latent heat of fusion. Okay, the latent heat of vaporization is always greater than the latent heat of fusion. You can also join our online tutorial classes for different classes. We have tutorials for students in SS1, 2, or 3. We also have for UTME candidates, for JAMB candidates, for students who want to write the JAMB or the UTME exam, and for those who want to have the post-UTME exam after the UTME exam, and also for candidates that are sitting for WAEC exam or GCE or NECO. And we offer this tutorial on various platforms, so you could join us on WhatsApp or on Telegram. It could be on Zoom or on Google Classroom. So we have various platforms where we take our tutorial. The links to join the platform are available on our website at scholar.com, or you could also check it out in the video description below. Next on measurement, a hydrometer is an instrument for measuring the hydrometer is used to measure density or relative density. Okay, relative density by finding the apparent loss in weight. Next, a transformer has 300 tons of wire in the primary coil and 30 tons in the secondary coil. If the input voltage is 100 volts, the output voltage is. Alright, so let ES be the EMF in the secondary coil, EP be the EMF in the primary coil, and from the question, that is also, you can say, the input voltage. Okay, we have 100 volts. Let the number of turns in the secondary coil be NS, and we have it here to be 30. So you have 30 turns in the secondary coil. Alright, while the number of turns in the primary, let that be NP, and here it is 300 turns. Okay, in the primary coil. Then we have this relation here. Okay, we have this relation here: ES over NS is equal to EP over NP. Or if you cross multiply, you can say EX NP is equal to EP NX. So we then substitute some of these things that we have here. Remember that what we are looking for is this ES, the EMF of the secondary coil. So you say ES times number of turns in the primary, 300, times EP. Okay, that's 30, times number of turns in the secondary, that is EP is 100, number of turns in the secondary is 30. So we have 300 times this is 300 ES equals 30 times 100 is 3000. Then we divide both sides by 300. Okay, so in the divide both sides by 300, the EMF in the secondary coil is 10 volts. So we've got 10 volts. Next on nuclear physics, the activity of a radioactive substance depends on the purity of that substance and its age. Okay, its half-life. Next on light, the speed of light in air is 3 times 10 raised to the power 8 meters per second. If the refractive index of light from air to water is 4/3, okay, from air to water is 4/3, then which of the following is the correct value of the speed of light in water? Okay, so when you have light moving between two media, okay, so let's say it is going from one medium, okay, let's say the original medium to like a new medium, then the refractive index of that light is going to be the velocity in the original medium over the velocity in the new medium. Okay, now in this question here, we have light going from air to what? To water. So that means that the refractive index is going to be the speed in air, because it is coming originally from air, over the speed in water, which is where is anything. Okay, so we have this here. Now, so they gave us the refractive index as 4/3, so we say n here, the refractive index is 4/3, is equal to the speed in air. The speed in air here is 3 times 10 raised to the power 8 over the speed in water, which is what we are looking for. So if we cross multiply this, okay, what are we going to do is the denominator here, use it to multiply the numerator here, and use this denominator here to multiply the numerator here. So I'm going to have this multiplying this 4 times VW is this equals 3 times 10 raised to the power 8. 3 times 3 here is just 9 times this. Alright, then we divide both sides by what? By 4. Now when I'm dividing both sides by 4, what I'm going to do is I'll only divide this 9 here by 4. I'll leave this 10 raised to the power 8 as it is. So I'll say 9 divided by 4, that is 2.25 times what I already have here, this 10 raised to the power 8. So I have 2.25 times 10 raised to the power 8. Next, on magnet and magnetic field. A magnet is moved through a coil of wire. The EMF produced in the wire depends on the EMF will directly depend on the number of turns in the coil. Okay, EMF depends directly on the number of windings or turns in the coil. Alright, the last question here. So we have a question on electrolysis. A charge of 1 coulomb liberates 0.003 grams of copper in an electrolytic process. How long will it take a current of 2 ampere to liberate 1.98 grams of copper in such a process? Alright, so in this question, give us the mass of the copper, right? The mass of the copper that was liberated as a 0.0033 grams. Okay, now that is the mass that was liberated with 1 coulomb. Okay, with 1 coulomb. Now they want us to find the time that it will take to liberate another mass, a new mass, that's 1.98. okay, if we use a current of 2 ampere. Now if you look at, for this first mass, they didn't give us the current and the time. They only give us what? Charge. Why? Because the charge is equal to current times time. So it's like they've already multiplied the current and the time together for this one. So give us that 1 coulomb for this here. That is your Q1. Let's say that's the quantity of it that liberated this mass, this first mass here. It's going to be equal to I1 T1. And that I1 T1 is what? 1 coulomb. They give us the charge directly. Okay. But yeah, they only give us this current, they give us this. So then what we are going to do is, we remember that M is equal to ZIT from Faraday's first law of electrolysis. That M is equal to ZQ or IT. You know, Q of course is equal to IT. So M is equal to ZQ, which is IT. Now this Z here is what we call the electrochemical equivalent of the substance, and it is a constant for that substance. It is a constant for that substance. So we are going to say Z is equal to, if you make Z subject here, we are going to divide both sides by IT. So you say Z is equal to M over IT. Okay. Now this M1 is the original mass. So we just say we are going to set up a relation here. We will set up a relation here that in both cases, in both of these cases, the first time when this mass was liberated and the second time when this mass was liberated, it was the same. This electrochemical equivalent did not change. Sure, you get? It's like saying that Z1 is equal to Z2, and Z is what? M over IT. So your Z1 is going to be M1 over I1 T1, while your Z2 is going to be M2 over I2 T2. And remember that your I1 T1 is Q1, which they have given us as 1 coulomb, the quantity of electricity as 1 coulomb here. Okay, so I've replaced this I1 T1 now with Q1, because you can see that for this first value here, they didn't give us current and time, they only give us the charge directly, which has already covered for these 2 here. Then we do our substitution. So the M1, the original mass that was liberated was this 0.0033 over Q1, the charge that it took, which was 1 coulomb, equal to the new mass that was liberated over the current, okay, that liberated that mass, 2 times T2. So we are looking for this T2 here. So when we cross multiply, what we do here is cross multiply. When you cross multiply this and cross multiply this, if you cross multiply this now, you are going to get 0.0033 times 2 T2. So if you do this times 2, you get is 0.0066. Then multiply this by 1, you get 1.98. That means I'm going to get is 0.0066 T2 is equal to 1.8. So now get my what? The value of my T2. I will divide both sides by 0.006. Okay, and that will give me 300 seconds. But if you look at the options that we have here, they are all in minutes. So that means we need to convert from what? Seconds to minutes. And to do that, we simply divide whatever we are given in second by 60. 60 seconds is 1 minute. So anytime I want to convert from seconds to minutes, I will just divide by 60. Let's say I have 60 seconds, for example, and I want to convert that 60 seconds to minutes. I'll just divide it by 60. If I divide 60 by 60, I get what? 1. That means that 60 seconds is what? Is 1 minute. But here I have 300 seconds, so I'll divide it by 60 as well. 300 divided by 60 will give me what? 5. Okay, that will give me 5. So I have 5 minutes here. Okay, don't forget to check out our playlist. We have different playlists. We have for full solutions to UTME or JAMB questions and in physics, chemistry, and biology. We also have for modular quizzes as well. Okay, we'll also have a playlist for post UTME or post JAMB exam, and also for crash courses in physics, chemistry, and biology. So don't forget to check out our playlist for the available videos. So that's it for this recording. Thank you very much for watching. Please don't forget to subscribe to our YouTube channel at ScholarFedu. Okay, like and share our content, and visit our website at scholar.com to practice UTME exam and modular quizzes for free. Thank you.